Okay. So as I mentioned, for the midterm exam, it will only be the first third of the course, which is like, I think the first page of the syllabus, like before AGN. Okay, so it will cover all this morphological classification and Jean's equation, collisionless Boltzmann equation, and concepts like that. Two-body relaxation, virial theorem, lensing. Yeah, but I'll not ask very sophisticated questions from lensing. In fact, from none of this. They will be mostly conceptual questions, and a lot of them may even come from the book questions that I have. Okay. So last time we sort of ended at some of these pairs of potential and f, the distribution function. They just like the potential density pairs for the sort of static mass distributions. We looked at these self-consistent solutions of the collisionless Boltzmann equation. You can actually go both ways. You can get an f and then find a phi, or given a phi, you can try to find f, and it's sort of a similar idea as the density potential pairs. Okay. So if you recall our first couple of lectures, we mentioned that the structure in the universe was seeded by tiny fluctuations at the beginning, which we see as the fluctuations in the cosmic microwave background. Because of self-gravity, those tiny fluctuations sort of grow and give rise to the structure like galaxies and clusters of galaxies and filaments and so on that we see around us today. So what happens is, so there is, on the larger scales, there is this Hubble expansion where things are moving away from each other. But if you have a slight overdensity in certain regions, this gravity due to the excess mass or excess average density pulls the matter back in eventually. So the matter which is in the influence of this excess density gets decoupled from the Hubble flow and collapses back toward itself. So there is something called the spherical top hat collapse in cosmology or sort of large scale structure, which sort of is a very simple model where you say that you consider a isotropic homogeneous FRW universe, and then you sort of consider a small sort of let's say spherical region which is slightly overdense. So what turns out is that if you solve for the gravitational evolution of such a system, this is exactly how it looks like. That if the mass distribution is symmetric, the outside mass does not matter. So you almost the evolution of that overdensity is as if you have an FRW universe which has a density larger than the critical density. If your density is larger than critical density, and if there is no dark energy, what happens is everything sort of collapses back. So that sort of is the simplest zeroth order picture of how halos form, right? Matter decouples from the Hubble expansion, falls back, and so there is this radius called the turnaround radius. Matter goes out. It's almost like throwing a stone up. It goes up, reaches a maximum distance, and falls back in. I mean, FRW solutions sort of have that sort of a simple interpretation. The same way, this overdense region, expands out maximum, and at the turnaround radius, it falls back. So all that potential and all that potential energy, all that energy when it falls back gets converted into the kinetic energy, and that sort of energy is dissipated from bulk motion into random motion, and that process is called virialization. So you create these virialized halos. Okay, so we are not going to go into details of these models, but this is sort of the picture, and the models are not that hard. If you know the solutions of FRW, solution of evolution of the scale factor in FRW models, it looks very, very similar. So it sort of forms the starting steps towards understanding large scale structure. Okay, so we will not go into it, but once a galaxy like the Milky Way forms, it is surrounded by other galaxies like Andromeda, large Magellanic Cloud, small Magellanic Cloud. The reality is not a spherical top hat collapse. You have substructure, which is more complicated than a spherically symmetric collapse. Okay, and of course details are very complicated. So what we are going to do now in a bit is so once you have this substructure falling in, how do these satellite galaxies and dark matter halos interact with the other galaxy or the bigger halo in which it is falling? Okay. Yes. Right, no. See, the thing is, the halo itself is a small object compared to the universe as a whole, right? So in the cosmological solutions, the dark energy actually dominates at the largest scales. So if you go to smaller scales, you can sort of ignore it. But in details, of course, it also affects the evolution. What you're saying is absolutely right. That if you want to do this precisely, then it's trivial to include dark energy too. Yes, exactly. It's like a local matter-dominated universe. The other thing that I mentioned earlier was this something called violent relaxation, right? When we are doing elliptical galaxies, and we were saying that these are very beautiful, almost very regular, smooth, a lot of times spherical structures. The question that arises is it because of two-body relaxation that stars have collided in the sense of small angle collisions, two-body processes, and thermalize their energy to produce this nice spherical-looking symmetric galaxy? That's not the case. The two-body relaxation time, even for elliptical galaxies, is very long. So you need something faster in order to convert all this directed bulk motion into random velocities. And that's something that I mentioned was something called violent relaxation. So during this process of structure merging, there are fluctuating and time-dependent potentials. And the whole Hamilton, the conservation of Hamiltonian and all this sort of breaks down. And what this stochastic potential does is it sort of randomizes the trajectory of particles and makes it very smooth, even though it is not expected to be smooth, naively speaking. Okay. And the other thing that we encountered when we were doing the collisionless Boltzmann equation was this concept of phase mixing. That is, if you start with a uniform patch in the phase space, because of the Hamiltonian motion of those particles, you form more and more smaller scale structure. It sort of gets shredded and shredded. So what we are talking about is not that microscopic small scale structure. When we're talking about distribution function, we're talking about a coarse grained distribution function, which is smooth in X and V in the phase space. Okay, so that was sort of a recap. So, right. So let me, not this one. Okay. So last time I briefly showed you this figure in the last class. What we are seeing here is an n-body simulation. Like, you just take millions of particles and populate something which looks like our Milky Way and Andromeda galaxy. Okay, and you put them, moving towards each other. Andromeda and galaxy are the two of the most massive galaxies in our local group. Okay, and Andromeda is moving towards us, unlike Hubble expansion. So it's not like, Hubble's law fails or something. It's just that this is peculiar velocity, right? The local overdensity affects local overdensity. Gravitational force due to local overdensity is larger than this effective Hubble force. Okay, so this is an n-body simulation, just has gravity, but it is done in it's not a direct n-body. It does not do gmm by r squared. What it does is it populates these galaxies with star particles. Each star particle is not an individual star, but a collection of stars, and it sort of is supposed to capture. Actually, can you close that? It's supposed to capture the large-scale macroscopic gravitational field. It does not capture the two-body interactions, for example, right? So these are collision-less gravitational n-body simulations. Okay, let's see. So this is at some early time. This is for total 3 giga years, I guess. So this is from Binney and Tremaine. This is just so. If they were point particles, they would do Kepler's orbits, right, around the center of mass. It's all well known. So basically, nothing will change in time once it just goes around each other forever if they are point masses. But they are not point masses; they are distribution of stars. So what happens is, if we just sort of move in time, this is how it looks like. These guys come close. This is the closest approach, and then they move farther away from each other. And you see these structures, very long structures. These are called tidal tails. Okay, what happens is, for example, this galaxy, the outer stars are less strongly bound, and the tidal force, if you recall your concept of tidal force is not the gravitational force. It's the differential gravitational force that acts across an extended body. So a point mass will not experience tidal force. If you have a point mass which sort of plunges into the black hole, it will not become a spaghetti and all that we are used to. It's the, it's like, if I pull you equally from all your, so suppose there's a hand and I pull the hand and the shoulder equally, there is no stress felt by your hand. It's only when you pull your, arm differentially relative to your shoulder that you feel the strain. In the same way, tidal force is what causes this shredding. And the tidal force is just the difference in gravitational force across the two edges of the body. Okay, so a bigger body for the same mass of the body experiences a larger tidal force because the difference in gravitational force across a larger distance is higher. So these are called tidal tails, and you see such examples in Hubble Space Telescope images of some of the galaxies. So these have developed tidal tails. The outer stars sort of have been sort of stretched into these long tidal tails. It sort of moves back, falls back in, and now after the second closest approach, it no longer goes back, right? So notice the difference between a collection of stars versus 2 points. If they were equal mass, if you put the same mass in a point object for these two, they will just give you trivial Kepler's orbits. But here, all this energy which was in this directed motion of these stars has been converted into the random energy of all these stars which are just thrown around everywhere. And eventually, you get some object which is like a single object, yet it does, you can see these nice features. These features remain because, after all, these are collisionless systems. They need not, like, uh, the nominal relaxation time for these is much longer. So you can have very complicated phase space structures lasting for a long time. For example, if you look at Gaia, if you have followed the Gaia results, in our own Milky Way, we can see remnants of streams which fell into, or a massive satellite that fell into Milky Way like 8 giga-years ago. Right? We can still sort of see structure associated with it because these are collisionless systems. Okay, so the upshot here is that this directed motion of stars is converted into random motion of stars because of this tidal forces and also the time-dependent gravitational forces which act here. Okay, so here are some examples of tidal tails. These are HST images, Hubble Space Telescope. So you see these are these look as if these are from that simulation that I showed you. So these are far away, and you can actually see this stretched tidal tail. These are closer, and you see these tails. And tidal tails are seen both in stars and in gas, because the differential gravity acts on both stars and gas. So here are some examples. Right, so the tidal force for a point mass goes like m over r cube, right? So basically, it's gm, the size of the body, divided by r cube, because it's the difference between the gravitational, so delta of gm by r squared gives you gm by r cube delta r. The delta r is the extent of the body on which you're calculating the tidal force. Okay, so the tidal force is proportional to mass by r cube, where r is like the separation between the two bodies. Okay, whereas the gravitational force is m by r squared. So what it says is that yes. If you have a point mass, the gravity at a point, capital R away from that point mass is gm by r squared, right? So if you look at a small, a body with a small extent delta r, the inner point is pulled by gm by r minus delta squared, and the outer point is sort of pulled by gm by r plus delta. So it basically is ddr of 1 by r squared times delta r. It's sort of Taylor series expansion around the center of mass, right? You got it? So this is the reason why moon is important for tides on Earth, right? But Earth's orbit is essentially not affected by the moon. For tides, in fact, moon is slightly more important than the sun, because even though mass of the moon is small, its r is smaller. The distance of the moon from Earth is much smaller. So that's 1 by r cube helps you creating these tides on Earth. Okay. So you can actually define a radius or an extent of an extended body. If a body becomes bigger than that, then the gravity that pulls and keeps this body intact can be overwhelmed by this tidal force, which tries to shred it. Okay, and this, what I'm actually doing is this balancing the tidal force due to a mass. There are two masses. They are distance d away from each other. Okay, let's assume that one of them is massive. The other is less massive and more extended. So I'm trying to find how big the size of this companion be for the tidal force to be able to shred it, right? So what I'm actually doing is I'm balancing gm by g capital M by r cube times delta r. Right? That's the tidal force I'm balancing that with g small m by small r squared. That's the gravitational force which is acting on the outer sort of surface. So if I balance those two, I get this. So the tidal radius divided by the distance between these bodies is about the mass ratio to the 1/3. Right? And this 1/3 comes from 1 by r cube dependence. Okay.
Can you repeat this RT by RD? Both are cube,
right? Right. So let's consider this extended mass, small m. Okay. So this is the center. So the difference. So what's the tidal force acting on this small m due to this capital M? I mean, that's just so gm by say r squared. Let me just call this r. This distance is small r. Okay. And I'm sort of doing a Taylor series expansion. So ddr times say delta r. Delta r is the size of this guy. Okay. So this is just minus twice gm by r cube delta r. This is the tidal force acting on, say, this point of this body. I'm actually dropping factors of 2, so don't bother about that. The scaling is more important. This can actually be done much more carefully. Okay, so this is the tidal force acting, which is trying to, stretch this point into a tail, right? But it is also experiencing gravity due to this gravitating object. So that force per unit mass is gm by delta r squared, right? Again, I'm dropping factors for. So if you equate these two, you get delta r by r going like small m by capital M to the 1/3. That is what I was actually trying to say. So that delta r threshold or the tidal radius is distance, which I call the d, so r and d I'm using, times the m to the m 1/3, right? If I equate these two, I get a delta r by r cube equals small m by m, and that gives me that. So this is the tidal radius.
So the delta is more than we get that.
Yes, more extended objects are easy to tidally break because the gravity is the same if you make it extended and extended, but the tidal force becomes larger and larger. It's proportional to delta r. Okay. Good. In fact, this is a very important concept. I mean, this applies for Earth's tides. This is sort of the order of magnitude. The tides are actually very complicated things to model and understand. But this concept is at the heart of this idea. There are things called tidal. I mean, I don't know if you have heard. There are events called tidal disruption events. Have you heard? Has anyone heard of these TDEs or tidal disruption events? So these. Yes. So some of the supermassive black holes suddenly brighten in optical and eventually in radio. And what is sort of thought is going on is some star comes very near the supermassive black hole, and it is tidally shredded because of this differential gravity of the black hole, and it forms an accretion. A massive. All that matter of the star is sort of spread out in a massive disk, which can actually increase the accretion rate quite a lot. So that's why it becomes luminous suddenly. So these are called TDEs. So you can actually see if the black. So the interesting thing about black hole is all the scales around black holes scale with m. The length scales around black holes scale with m. So this distance, if you express in terms of the black hole mass, it turns out that stars around massive black holes do not experience as big a tidal force as around lower mass black holes. So black holes of 10 to the 6 solar masses are very, are very good at shearing and causing TDEs. On the other hand, massive black holes like a 10 to the 9 solar mass black hole, the tidal force on the star is smaller compared to the gravitational force, because this m here also appears here, right? Because if you express the distance between stars and the black hole in terms of Schwarzschild radii, this is like, say, 100 times the Schwarzschild radius. Then what I'm saying is what happens. So more massive black holes, stars are eaten as a whole rather than getting disrupted into an accretion disk, which powers a luminous burst, right? So it's actually a subtle but very important point. So if you see a TDE, and if it is like a normal star, then you know whether it's possible to get a TDE for that mass, supermassive black hole. Anyway, I will not go into detail, but I thought I'll just mention it since it's related. Okay, so this is fine. So now we'll do some estimates. Okay. So we'll do galaxy collisions, like what we saw that I showed you the simulation of. Okay. Okay, so let's see. So you have a star of small m mass, and say there is a galaxy of mass m. There is a relative velocity between these two of capital V, and the impact. So this kind of a calculation we are encountering for the third time. Gravitational lensing, you remember we were doing the photon and doing this. Then we did two-body relaxation, and now we are sort of doing almost a similar calculation here for a galaxy interacting with the mass with the star in other galaxies. So this appears also in free emission. So basically, this is a fundamental thing, because 1/r² forces are, the most common forces are of that kind, gravitational and electrostatic. So that's why it appears so much. So this is the impact parameter B. So this is a galaxy. It's interacting with the star of mass m, and we are in this impulse approximation. That is, the galaxy is not perturbed much from its original path, and the interaction is not very strong. So what is your delta V perp? The change in velocity in the perpendicular direction of this galaxy interacting with a single star, that's equal to twice Gm by BV. We have seen this, right? Yes.
So in this we need to build an approximation to see whether the galaxy is fixed and the mass is like the impulse approximation will be included in the equation.
It's one and the same thing. Essentially, we. That's correct. Right, but our interest is actually how does this galaxy get affected by interacting with a lot of these particles in the galaxy. So that's why this is, the calculation is the same, but that's why we want to sort of formulate it in this way. We want to ask, if this galaxy is moving through a collection of stars, how does it lose its directed velocity? So we'll first consider one particle and then see a bunch of particles. How many particles are needed in order for it to get deviated from its path? That's where we are going. Okay. This is nothing but f perp dt by m, right? We have seen this, the impulse approximation. Uh, so so first case is if the galaxy size RC is much less than B, right? The extent of this galaxy is smaller than this impact parameter. Then you can actually treat this as a point mass. So, okay. Galaxy like a point mass. Now the other one is the impulse approximation, which we are saying if V squared is greater than twice G M plus M by B, right? So it's moving much faster than the escape velocity from this system. We have actually seen that earlier as well. So then you'll have small deflection. Okay. This is equivalent to saying that B is much greater than RS, where RS is equal to GM plus M by B squared. Yeah, sorry, this RS is the sphere, strong encounter radius. Okay, we have actually also encountered this. Yes. Right, but that's correct. So we are considering this. See, the real problem has to be simulated. These are all like, under certain regimes, you can build some sort of a mental picture. That's why we had this M31 and Milky Way collision simulation, because the full problem cannot be solved analytically. But in certain regimes, you can actually get very good insight using these estimates. Okay. So this is your delta V perp. This is it. So this is what we have to. This is the key. So this is the velocity kick that the galaxy gets when it encounters with this mass, small mass m. So the small mass m in turn gains equal and opposite momentum, right? Because momentum is conserved. So let's calculate how much does the kinetic energy of the galaxy changes, so this is the change in kinetic energy of the system. So initially you have this galaxy moving with V, right? So there is no perpendicular kinetic energy in that state. After the collision, the galaxy gains a little bit of V perp. Also, the star gains quite a lot of V perp. So what is the change? So this perpendicular kinetic energy comes at the expense of this kinetic energy in the parallel direction. So this of the system is half m delta V perp squared plus half m capital M by m delta V perp squared. So this I'm just writing by momentum conservation, right? Capital M time. So in the perpendicular direction, the momentum should be conserved. So the delta V perp of the star should be capital M times delta V perp of the galaxy divided by the mass of the star. So this is the kinetic energy gained by the star. And you can actually see that this is much more than the first term. right? This is actually a well-known thing about collisions, right? If you have a system, if you have a collision between, if you have a two-body process, most of the energy, kinetic energy, is carried by the lower mass particle. So the same thing is what we are seeing here. So if you plug in VPerp from here into this, what do you get? So this is equal to so capital M times twice G squared small m squared by B squared V squared plus M squared by M twice G squared M squared. So basically this term is larger than this term by capital M to small m, by the mass ratio. This is the kinetic energy in the perpendicular direction of the star is larger by small m by capital M by small m. And the total energy is equal to twice G squared M plus small m, M by B squared. So this is the gain in a single encounter. This is the gain in a single encounter with impact parameter B. This is the gain in the perpendicular kinetic energy. But this energy has to come at the expense of the parallel kinetic energy, right? Because the total energy is conserved. So half capital M V squared should be equal to the gain in kinetic energy in the perpendicular direction plus, let's see, the galaxy's velocity after the collision becomes V plus delta V parallel. This delta V parallel will of course come out to be negative, but let's just write it as this. So after collision, this is the velocity in the parallel direction plus half capital M V plus delta V parallel squared plus half small m capital M delta V parallel. Again, by momentum conservation, the delta V parallel, the parallel velocity change for the small particle will be capital M by small m. So I'm just using that. Okay. So if I sort of expand this out, and if I assume that delta V parallel is much less than V, in a single collision, your galaxy does not lose a lot of its parallel velocity, which is a very reasonable approximation. Then if we ignore the quadratic term, basically these delta V parallel square terms, and just retain the linear terms, right? Then what we get is minus of delta V parallel is equal to delta of KE perp divided by capital MV. Right, so you'll have this 2 times capital MV delta V parallel, and that essentially that's what you just retain. So this is what you get. So if we plug in, that's what we get is 2 times G squared M times capital M plus small m by B squared VQ. And what is the change in kinetic energy for small m? That's just half times capital M by small m times capital M delta V parallel square. Right. This is exactly, this mass proportionality comes from momentum conservation. And now we have the expression for delta V parallel here. So if we plug everything in, what we get is half m capital V squared. So now we have delta V parallel by V the whole squared. That's just twice G squared m times capital M plus small m by V squared V cube the whole square. Right, so I'm just sort of plugging this in from here in this. Times capital M by small m 1 by V squared. So this capital M by small m is just that. I mean, there are some manipulations that are done, but you get this. So you can actually write it as half times m V squared times capital M by small m times 4 times Rs by B to the 4. So this is just, this Rs is just this, right? The radius of strong impact parameter corresponding to strong interaction. So when the impact parameter is smaller than this value, then the deflection is large. If your impact parameter is more, then it's sort of a tiny deflection. So if we plug, if we sort of express things in terms of that, this is what we get. So this is change in kinetic energy for in the parallel direction for capital M is just retaining only the leading order term. That's just mv delta v parallel, right? Because we are ignoring the delta v parallel square terms, because delta v parallel is small compared to capital V. So this is just equal to mv squared times twice g squared m capital M plus small m by v squared v to the 4. This is equal to, again, if we write in terms of Rs, this is twice Rs by B the whole squared. Okay, so but where is my dimensional? No, times mv squared, right? Because this is a dimensionless thing. So we actually have to compare this and this. And basically what we are asking is, where does this parallel kinetic energy go? Does it go into the massive guy or to the star? And it depends on this ratio Rs by B where it goes, right? So, so delta Ke for small mass m is small compared to delta Ke sort of parallel. So there is a difference between parallel and perpendicular scaling. In the perpendicular direction, it's always the small mass which will have more energy. In the parallel direction, it depends on this Rs by B ratio. That's correct. So if Rs is far less than B, then this is small. So this guy will dominate. So what happens is the perpendicular energy for the stars comes at the expense of this energy from the massive galaxy, right? So that this is where we are going essentially, that the parallel kinetic energy of this galaxy gets converted into the perpendicular mainly of the stars. So what happens is if you have a star thrown into collection, if you have a galaxy thrown into a collection of stars, that parallel kinetic energy of that galaxy gets just converted into the random motion of the stars. And that's what we roughly also saw in that simulation, that the Kepler's orbits sort of shrunk, and all this energy went into the mess that was created in stars. Okay. If capital M by M Rs by B squared is much less than 1. I mean, this is essentially, I'm just saying this is much bigger than that. And this is valid when Rs is small compared to B, or if B is smaller, B is larger than your Rs. Okay. Or Rs by B squared is much less than all M by M, much less than 1. So this we are anyway assuming small m by capital M much less than 1. That's, a star is of course much less massive than a galaxy or a globular cluster or whatever. Okay. So the interpretation is, typically the kinetic energy of galaxy is dissipated into random kinetic energy in the perpendicular direction of stars. Okay. So again, we have actually, if you see in the two-body relaxation, we also assume this bath of stars to be uniform. Here also we are sort of assuming the same thing, but a real galaxy has some extent and so on. So these sort of estimates break down beyond a size which is bigger than the size of the system. Only for scales smaller than the size of, say, the globular cluster or whatever, or a galaxy that we're talking about, can you assume the density of the stars to be constant. Okay. So again, the same procedure. Here we have looked at this exchange of energy for a single collision with the given B. Now we have to integrate over all possible impact parameters, right? Let's see. So let's just write dv parallel by dt. This is the rate of change of parallel velocity of a galaxy. This is equal to, let me just write down B min, B max. This impact parameter, this concept appears everywhere, so it's a good idea to learn this once very well. It will help you in various places. Okay, so this is n times the velocity. So this is number of stars per unit volume. Okay, let's assume that there are stars with this density. This is the velocity of this galaxy. Then this is twice g squared m times m plus small m by b squared v cube. Also notice this 1 by v cube dependence that was there in the collisions as well. This is nothing but delta v parallel, right? Delta v parallel for the galaxy. We actually derived it here. Where did it go? Yeah, here it is. So I'm just plugging that in, g squared, and yeah, I'm just plugging that in, right? That's delta v parallel times 2 pi b dB. So if the stars are all uniformly distributed, the number of stars in annulus of cylindrical radius b is just 2 pi b dB times the number density. So the flux of, the number of stars which lie in this impact parameter range is nothing but this number density of stars times the velocity of this projectile times the area of this annulus. So this is number of stars per unit volume. This is area. So flux times an area is number per unit time, and this is the change in velocity in the parallel direction for the galaxy. So this is, if you average over all possible B's, this is what you get for how fast will your parallel velocity get dissipated. Again, this B and this B sort of cancels. This also appears everywhere. You have this logarithmic integral, which gives you log of this Coulomb parameter, right? So, so this, if you integrate it over B, what you get is, so this lambda is equal to B max by B min. So what is B max? B max should be the size of the stellar system in which the projectile galaxy is running into, right? And B min should be RS, right? This radius below which the deflections are very strong, and this whole approximation breaks down. So again, the same. The nice thing is what you have at the end of integration of all this is log lambda, and log of anything, even very, very big. If you make a huge mistake in estimation of B max and B min, your log of that will not be such a bad approximation. Okay, that's the nice thing about the logarithmic dependence. Okay, so this is what you will get. So what do we have? So if number density and this just comes out. This is twice G squared M, capital M plus small m, by B cube. 2 pi times log of lambda. Okay, so you see, right, I think this is correct. So here, what we are assuming is that these stars do not have random velocities. Normally, the stars will have the virial velocities of that stellar system in which they are lying. Here, we are assuming them to be cold. That's why you're just sort of using a constant density of stars. In fact, if you do it more carefully, this actually should be replaced by F d3v. Right, so you have to integrate over all the possible velocities of these stars. In fact, this is like the relative velocity between the stars, and we are not going to do that. Okay, the key takeaway. So, but it's good to remember. It's good to know what the formalism is. So this is some sort of a friction force, right? You throw in a projectile, and your directed velocity gets dissipated because of this sort of a drag force. Is this, yeah, this sort of a drag force. And the other thing about this force is that it goes like 1 over v squared. So if you have a fast galaxy zipping through a stellar system, it will not stop. If you have a slow galaxy, it will lose a lot of its energy. So that's why in this simulation that I showed, the first encounter more or less does not break that the I mean, it does not distort and dissipate it right away. But in the first encounter, it loses some energy. In the second, it sort of approaches with a lower velocity, and the lower the velocity gets, the faster it's sort of it's dissipated. Okay. So these things are still useful for you to build intuition, even though you can do numerical simulations. Okay. So this is called, this kind of force is called dynamical friction. Sort of like a viscous drag in a fluid, right? We have a Stokes, if you have a Stokes fluid, you have 6 pi eta AV as the drag force. This is proportional to V, it's proportional to minus V. So if you drop a ball bearing into a column of liquid, it will reach a terminal velocity. And this is the force that acts. So it's a similar thing, but it's totally different from the physical point of view. This happens because of gravitational interactions between the stars and the galaxy. Whereas this is just due to fluid viscosity. So if we, so this is assuming cold stars. They don't have thermal motions. If we do this formula more carefully, then we have that distribution function guy, okay? And if, so for, so let me actually, for V much less than, or less than sigma. So sigma is velocity dispersion of stars, right? This collection of stars on which you throw a galaxy. This is the velocity of approach of the galaxy. If the velocity of stars is bigger than the velocity of approach, then you can actually imagine, right? They have a random motion of their own, which is very large. So it won't feel as much gravitational influence of the projectile of the galaxy. Okay, so in that case, for this case, if you do this procedure of integrating over the distribution function, which I was mentioning here, right, what you get is a dV by dt is proportional to minus V parallel. So just like the drag force, this is just like a Stokes drag, right? So here we had 1 by V squared. Now here, if the velocity of stars, the random velocity of stars is larger, then the faster guy experiences more dynamical friction than the slower one. Or as opposed to the previous case, there, if you have a faster, if your sigma is much less than V, the fast moving projectile just sort of passes without getting much disrupted. So there is a, let's see, there is a, so this is the equation for dV dt. This is not the force. This is force per unit mass. So what is the, what is the friction force that you multiply by capital M? Now, if you multiply this by capital M, what you see in both these limits, here and here, the only difference is that the velocity dispersion of stars. Now, what you say is the friction force, dynamical friction, which is defined as minus m dV parallel dt, is proportional to, I mean, we can ignore this small m relative to capital M. It's proportional to m squared. And then there is a velocity, dependence v or v to the minus 2, depending on whether sigma is It should be really capital V. That's what I'm using. Depending on whether sigma is less than V. Sorry, no. This is -2. So this applies when sigma is greater than V. Sigma is greater than V, and this applies when sigma is less than V. Right, so this is actually interesting. The more massive an object is, the higher the force it will face. In fact, the acceleration is proportional to mass of the test particle itself. We are not used to this kind of a thing very often, right? For gravity, for this, like the simplest two-body gravity, acceleration is independent of mass of the object. The thing to notice here is that acceleration is actually the deceleration actually is proportional to the mass of the projectile itself. The more massive the galaxy is, the faster it will lose its directed motion and sink to the bottom of the potential. So what is the reason that massive things like massive stars and the black holes all go towards the centers of potential well? I mean, you have galaxies merging, right? There are galaxy mergers, but most of the time we say that the AGN sits in the center of the galaxy. It's because of dynamical friction. The time scale for the dynamical friction is proportional to 1/m. So if you have a very massive galaxy, it will sink to the bottom. It will lose its directed motion and sink to the bottom of the potential well the fastest. This is an extremely important thing, and that's we sort of take this for granted that, oh yeah, if you have a dark matter halo, the elliptical galaxy should be sitting at the center of that dark matter halo. We forget that there were mergers and so on which brought that elliptical galaxy into the halo. Now, this is actually an important question. Why is it at the center? I mean, it came from somewhere. The reason it is at the center is because it is the fastest to dissipate its directed kinetic energy compared to a lower mass star, a lower mass galaxy. It's an extremely important point. That's why massive things in gravitating systems are at the centers of the potential. Okay. Similarly, in globular clusters, most massive stars and most, these compact objects like, low mass X-ray binaries, the massive guys are more concentrated towards the center. The low mass stars are just kicked out. And, in order to, they're kicked out, they take away the kinetic energy and make the system more and more bound. What is remaining behind becomes more and more bound. So it's sort of a, there are these different, all these are gravitating systems, right? The fundamental force here is 1/r². But we are talking about collection of stars, right? Rather than individual stars. So it sort of gives rise to this kind of an emergent behavior, which is different from the microscopic law of force. Okay. So there is a famous formula. So there is Chandrasekhar's famous dynamical friction formula, and that's based on this, velocity space integration and all that. We're not going to get into that, but this is a commonly used formula, which has this nice thing, which you should always remember. Okay. So what about the intuitive picture? The intuitive picture for this is, so you have a massive galaxy, let's say this galaxy, and there are stars moving randomly in different directions. It has some sort of a sigma. Now, so you have this galaxy. If you have slightly more stars on the right, which are moving in the left direction, so, or in other words, if the galaxy is moving relative to the center of mass of the stars towards the right, then so what happens is these stars sort of get somewhat deflected, right? On average, they have a tendency to, if you go to the rest frame of the galaxy, these stars are biased a little bit more. There are more stars which are going to the left, and they are sort of concentrated a little bit in excess in the wake of the galaxy behind the. Similarly, there are these stars here which are going in randomly in various directions. They also get enhanced a little bit here. But if there is a bias of this velocity, there are more, if the bulk velocity is negative, of stars is negative, there is an excess of mass here compared to here in the front. Now, this excess mass is what is pulling this back in and slowing down the galaxy. This is sort of a physical way of looking at the dynamical friction, right? If you have particles, forget about the random velocity in the other direction. If you have just parallel velocities, you have, you will, if you have a, if you have slightly higher, higher velocity here, you will have more, a larger agglomeration of mass here, and that this excess pull is what slows down this galaxy. Oh, in fact, I have written down the Chandrasekhar formula. Let me just write down if we have it. So d dt of velocity of mass m is equal to minus 16 pi squared log lambda g squared small m capital M plus m. This is what you have, u0 to vm. Vm is the velocity, Vm is the book from where I have taken, V is Vm. Okay, to Vm, F, V small m, V small m squared dVm. So this is that phase space integral over the relative velocities between the galaxy and the stars times Vm by Vm cube. So this is the formula. Now, when Vm is much less than sigma, this will give you something which is proportional to Vm squared. And if Vm is much greater than sigma, this will give you a number. That's why you have the previous dependence that I was talking about. Okay. So this is the end of the portion for the exam, which is on Friday. Now, in the rest 15-20 minutes, I'll just talk about the next topic. So, any question? This concept is extremely important, and it should stay with you. You will be able to understand, most of these macroscopic features that you see in galaxy simulations. No questions? Okay, so I'll actually.
I'm sorry.
Yes, Shaikh.
How you come up with the time scale?
The dynamical, the friction time. Okay, yeah. Sorry. I should, yeah. So this time scale is defined as velocity by dv dt. I know that. I'm sorry. Yeah, it's an obvious thing, but yeah, I should mention it. If you have a velocity v, the velocity divided by the rate at which the velocity is changing defines the time scale, and this is proportional to m. Good. No. Okay, we are here. So we already talked about this. Okay, so the next topic is, now I'll is active galactic nuclei. So till now we were talking about galaxies, and galaxies traditionally are a collection of stars, right? And they are these diffuse collection of stars, and they are diffused because the size of an individual star is much smaller, but the capability for us to resolve things is much weaker. So you see it as a smudge rather than delta functions of stars in the sky. AGN, so traditionally galaxies are a collection of stars, but slowly and steadily we have actually realized that galaxies most of the galaxies have supermassive black holes at their centers. Okay, and that makes a huge difference for the evolution of the galaxy and for the other properties uh, of galaxies as well. So active galactic nuclei, or AGN, are a class of galaxies which can show activity at their centers. And this activity is powered by accretion onto the central supermassive black hole. Okay. In fact, there were some galaxies discovered as early as 1910s, which showed spectra which were very different from spectra of normal galaxies. Spectra of normal galaxies, as we briefly discussed, are dominated by absorption features due to stars, whereas the spectra of these weird galaxies that someone called Seifert put together had strong emission lines, broad, strong emission lines. So we had this classification already even in 1920. But what these things are, people didn't know until 1960s, late 50s, that these things are, very important, and they're extremely powerful. Okay, so that's what we are going to talk about in the next few classes. So let me actually show. So AGN. So there is like a zoo of AGN, active galactic nuclei. Sometimes you see active galactic nuclei in optical, you see it in radio. Basically, AGN show a broadband emission. Unlike stars, which are black bodies with absorption lines, the AGN are broadband emitters. They emit from low frequency radio all the way to gamma rays. Okay, so with the advent, so our traditionally optical is what people could do things, but then progress in radio and gamma rays and everything just sort of showed that all galaxies have AGN in them. Okay, so here is an example of a quasar. Quasar is a type of AGN. Quasars are bright in optical. So here is an image, Hubble Space Telescope image of a quasar. And this is basically a point source. So that's why they are called quasi-stellar objects. They are like stars. They are point sources. Okay. So this is an image sort of, of a galaxy. We cannot see the galaxy here because the central source is so bright that, there is no way you can see the dim galaxy around it. And it has a luminosity which is larger, not just the brightness at that point, but the luminosity is larger than the luminosity of the entire galaxy. Right? You know the difference between brightness and luminosity. For example, a star is extremely bright, but it's not as luminous as a galaxy, right? Because it's extremely bright because all that light is concentrated on a very small solid angle. But here is an object which is not only bright, but also extremely luminous. It's more luminous than the galaxy in which it resides. Now, if you're able to block somehow the light from this central source, which is what is done here in the image and right, you can actually see the underlying galaxy. Right? You can see it's sort of like a spiral-like, disc-like galaxy. And this is blocked. The central light is blocked by something called a coronagraph. Coronagraph is an extremely, it's a versatile technique. For example, if you want to detect the corona of the sun, you want to block the extreme light coming from the sun. And there is this Aditya L1, which is a coronagraph, which was, one of the instruments there is a coronagraph, which was launched recently to observe the sun. So you want to block the light from the sun and look at the corona and other magnetic processes in the diffuse part, which is dim and not observable otherwise. So this is a similar concept. Similarly, you want to detect planets. You want to image planets around nearby stars. How do you do that? The star is extremely bright. So you want to put a coronagraph and block the light from the star so that you can see the reflected light from the planets. So this is also used for planet hunting. Okay. So this is about quasi-stellar objects. These are extremely luminous and bright objects. And all this light is coming from the size, the emitting region is of order the size of the solar system. Imagine this, the solar system emitting more than the entire light of the Milky Way, the scale of the solar system. So it's extremely, the energy density of this thing is extremely high. Okay. Now the key question arises, how are these powered? Where do you get so much energy in such a small volume? And the ultimate source of this energy is gravitational power, right? Or accretion power. And the efficiency of accretion power can be extremely high. If you are able to accrete mass m onto a black hole, you can actually extract out about 0.1 mc squared of the mass that you have accreted onto the black hole. So the efficiency, you will see this number almost always used universally, that the efficiency of accretion is about 0.1. Okay, now and how do you get it? Actually, let's see. So I asked the office people to put the clock there. Otherwise, I have to rely on you guys, and that's not. I'm going to tell you what, how do you explain this 0.1 as the efficiency of accretion power. So you have a black hole here, and you have a test particle at infinity. So the system has energy 0, right? You have two masses which are separated. Now what you do is, if by some process, if you are able to bring this test particle and put it in an orbit around the black hole, you have reduced the energy of the system, right? The total energy of a bound system, from virial theorem, we now know that energy equals half of potential energy, right? So the potential energy is negative, half of potential energy is also negative. Initially, you had a system which had 0 energy. Now you have a system which has negative energy. Where did the rest of this energy go? Okay, in order to make something bound, you have to dissipate that energy, either into radiation or into some other sort of smaller stars which take away the kinetic energy and make the remaining system bound. Okay, so let's see. So if you have a circular orbit around a black hole of say a radius r, the orbit is small r. So the energy is equal to energy per unit mass is minus gm. Capital M is the mass of the black hole by 2r, right? Because this 2r comes because there is potential energy, but it's also going in a circular orbit, so it has a kinetic energy. So this is your total energy. Now, initially when the particle was at infinity, it had 0 energy. So the energy that is in principle available for you to radiate away, this energy, if you radiate away, is what will facilitate this infall of matter. So this energy per unit mass is just gm by 2r. Now, if you look at the solution of orbits of test particles around black holes, and if you do it for a non-spinning black hole, what you'll realize, so essentially, let's say you have a this particle very far away and sort of almost goes in a circular orbit, say due to say friction or whatever, it slowly spirals in. Okay, in GR, so in Newtonian gravity, if you have a point mass, it will just keep spiraling in and then go to the center. In GR, there is a special radius which is called the ISCO, innermost stable circular orbit, ISCO, within which there are no stable orbits. So you have this particle at large radii which almost goes into in circular orbits, but as soon as it comes closer by losing angular momentum and it hits ISCO, it will just plunge into the central black hole. And it turns out for a non-spinning black hole or a Schwarzschild black hole, our ISCO is just 6 gm by c squared, where my m is the mass of the black hole. Now, what it means is that the minimum value of this r can be this. So if you, yes. Yes, it will just plunge radially inwards. So that's basically, after that you cannot draw this energy. It's just plunging. So the energy, the maximum energy that you can draw from accretion is basically till this radius. And if you plug that in, you have gm by 2 times 6 times gm by c squared. This is energy per unit mass. So this is just about 1/12 of c squared. That's where this 0.1 comes from. Okay. In fact, if you have a spinning black hole, the ISCO is further in, and for the maximally spinning black hole, ISCO is same as the Schwarzschild radius. So if you average over all sort of spins, or do some adopt a typical number, people mostly adopt 0.1. So for every mass m accreted onto the black hole of mass capital M, you get small m c squared times 0.1. Okay, so this is the source of accretion power. I mean, accretion is a topic in itself. There are a lot of interesting physical problems associated with accretion. One of them is, how does this matter, which is going around in circular orbits, lose its angular momentum and slowly spiral in and get accreted so that it can release energy? Because these are sort of like Keplerian orbits, right? If you have a point mass, a black hole, and you have test particles which are going essentially in circular, and we are assuming circular orbits because gas is very dissipative. Gas is able to radiate away all its energy except the one which is associated with its angular momentum, right? So, if you look at this effective potential as a function of r, right? This is phi effective. And if you start with this energy, the gas is able to get rid of all this energy and eventually sort of settle here. Right, so even if you have an elliptical orbit of the gas at the beginning, it will just radiate away all its extra energy, but maintain its angular momentum in absence of some process, some physical process which helps, which sort of acts like friction. And this is the famous angular momentum transport problem of accretion disks. So angular momentum transport. So how does matter lose its angular momentum and slowly spiral in? And what people think now, the present understanding is some sort of MHD turbulence is responsible for fast angular momentum transport. If you put in molecular viscosity, right? Now, if you have friction due to viscosity, that is just too small. Okay, so some sort of turbulent transport is necessary for this to happen. Anyway, for us, the key takeaway from this estimate is 0.1 mc squared. So for every m accreted onto the black hole, you get a radiation with, and this power can come out as outflows as well. For every mass m accreted onto the black hole, roughly 0.1 mc squared is available for us as energy, dissipated energy, which can either be radiated away or put out in form of outflows or jets. Okay, let's get back to the presentation. So this is where this efficiency comes from. In contrast, stars' primary energy source is nuclear fusion happening in their cores, right? And this is basically this, for every mass m undergoing nuclear fusion, right? The delta m, the mass defect between products and reactions, is about this much. If you do a PP reaction that's happening in the center of the sun, and if you look at the difference in masses of the products and and the nuclei which are fusing together, that's about 0.007 mc squared. So the efficiency is much much less. And the other thing is, it's even lesser than this, because not all the mass of the sun will burn in the age of the universe, right? It's only like a small fraction of the mass of the core will be burning. So only the most massive stars, which live only for 10 mega years or a few tenths of mega years, are able to convert this nuclear energy efficiently into substantial power. But most majority of mass is in low mass stars. So this 0.007 is for every mass m undergoing PP reaction. But remember, only a small fraction of that mass, which is in the massive stars, is able to produce this energy on a short enough time scale. So the efficiency is even smaller than this. So you say for a standard initial mass function, or IMF, only one supernova happens for every 100 solar mass that goes into star formation. So that brings in a factor of 10 to the minus 2 right away. If you say that only the stars which undergo supernovae are doing this fast enough, whereas in accretion, it can actually happen very, very rapidly. Let's see. Okay, so I already showed the scalings. So AGN. So for this material, I'm actually following this Schneider's book, which I had mentioned at the beginning. So this is these are 3 images of a Seyfert galaxy. You remember I said that there were these emission line galaxies which were known in 1920, and they were studied by someone called Carl Seyfert. So those galaxies are known as Seyfert galaxies. So they look like spiral galaxies normally, but they have very bright centers. And these bright centers are active galactic nuclei, or AGN. These are powered by accretion. So this shows 3 images of this Seyfert galaxy NGC 4151. And this is very short exposure and longer exposure. So in the short exposure, you only pick out the brightest things. So you pick out the center of this galaxy. This is the AGN. It's very bright and small. But if you expose it long enough, you can sort of pick out the whole galaxy. This is not a quasar. Seyferts are much dimmer than these guys. These are quasars. They're extremely powerful. These are less. So that's why you can see in the same frame, the spiral galaxy. So if you look at the extragalactic background, so this is also a slide from an early lecture of mine. This is all the radiation that you see, that you observe in the universe, going from low frequencies to the highest frequencies. Okay, stars are here in visible and UV and IR. Dust is here. Dust radiation comes from, dust radiation is also thermal radiation. Dust particles are also black body emitters, essentially. And they sort of just absorb light from the stars and, say, even quasars, and re-radiate it. So all the radiation from stellar processes is just concentrated in this narrow wavelength range. Then there is the CMB. CMB is the highest energy density of all the radiation components. This has to do with cosmology. And then there is radio and this gamma ray and X-ray emission that's dominated by AGN. So you see there are like 3 essentially totally different sources of this broadband radiation that we see. The accreting supermassive black holes, or AGN, here and here. At the smallest wavelengths and the highest wavelengths, the accretion dominates. In optical, it's the stars. That's why traditionally galaxies were equated to stars. The optical is where we could see things the best. And the CMB comes from the early universe. Okay. So these are those galaxies that I was mentioning to you about, these Seyfert galaxies. Seyferts are low power AGN, unlike quasars or quasi-stellar objects. They show emission lines, broad and narrow emission lines. So here are the emission lines that I was talking about. So this is the observed wavelength, okay? The wavelength measured by your telescope here. This is a Seifert at, very nearby Seifert, essentially redshift 0 Seifert, 0.009. So this is 0.003. So these, essentially the lines that you observe here have the rest wavelength. They're observed at the true wavelength of these lines. And these are emission lines, as I mentioned. Seiferts, unlike galaxies, have emission lines. These are broad lines. You can see that the velocity spread is broader in this Seifert compared to this one, right? They are narrow lines, like H beta here is a narrow line compared to here. Similarly, this H gamma, right? H alpha, beta, gamma, n equal to 3 to 2 is H alpha. H alpha is outside this. H alpha should also be bright. So it's at 6,600 something. There is H beta, H gamma. So these have broad features. These don't. These only have narrow lines. So these are the Seiferts. So these are called type 1. Type 1 Seiferts show both narrow and broad lines. Type 2 Seiferts show only narrow lines. And in contrast, a quasar is much brighter. This is at redshift 2. Redshift 2 is very far away. You're still able to see the spectrum. That means it's inherently very bright. And here you see very broad emission lines as well. And it's sort of not that dim. You see the numbers, scaled values for the flux are only slightly smaller than this. If they were the same luminosity, this should have been much fainter. So this mainly shows broad lines. Now there was a lot of information like this collected by observers, and like there were type 2s, type 1s, this, that, all of this was put together as just like classification. Then people realized that we are actually looking at the same system, but from different viewpoints. So all of them are essentially supermassive black hole powered phenomena. We are seeing different manifestations depending on where we are observing this system from. So this is AGN spectra. The defining feature is a background continuum. You can see this continuum, right? The part of the spectrum where there are no strong lines. That's the continuum. And on top of that, you have these emission lines, okay, narrow and broad. In contrast, if you have galaxies, so these are 4 different galaxies spectrum. So this is an NGC 4889. It's an elliptical galaxy. You see these absorption features like a Balmer break and all the standard features, which is sort of a combination of stellar absorption features, is seen in a galaxy spectrum like this. This is a SA galaxy, slightly more disk towards the disky side, but this also only has absorption features. This is slightly bluer perhaps than this, because its SA is more likely to be bluer. Now these are galaxy spectra of different types, dominated by old non-starburst galaxies. These are old and non-starburst galaxies, which are dominated by absorption features. Right? They're not going a lot of star formation presently, whereas these are also galaxies. At the bottom, these are also galaxies, but these are star-forming galaxies. They have these narrow lines. So, versus AGN, these lines are extremely narrow. Can someone give a intuitive reason why the AGN can have broad lines? So let me actually give you a hint. Broad lines reflect the deep potential well. So yeah. Not quite gravitational redshift. Yes. So it's a deeper potential well. So the random velocities and also the circular velocities of gas going around supermassive black hole can be much larger than the velocities on the photospheres of even massive stars. You don't get, velocities larger than, 100 kilometer per second for stellar photospheres. So that's why these lines will always be narrow. And even the narrow lines here are much narrower than the so-called narrow line regions here. Okay, because of that. These lines, the other difference between these lines powered by AGN and these lines powered by starburst is the ions which are prominent. The stellar radiation is, optical UV a little bit. It's dominated by lower energy starlight, whereas quasar radiation or the AGN radiation is harder. It has X-rays and gamma rays and so on. Harder radiation can excite higher ions. For example, it can actually excite very highly ionized species of oxygen, like oxygen 6, right? Whereas H2 regions, these ionized regions around massive stars, do not have photons which are larger than an EV, right? They don't have photons much beyond UV. So they can only excite low ions. They can only ionize and excite low ions. So by measuring these line ratios, like by basically trying to understand what is exciting these transitions, you can get a sense of the nature of the ionizing or the radiation field in which these atoms and ions which are emitting these are exposed to. There is something called BPT diagram. I'll actually be using a little bit of these terms. So this Baldwin, what is PT? So this BPT diagram is like ratio of different lines. Flux is measured at different lines, the galaxies lie somewhere else, AGN lie somewhere else in these emission ratio plots. It's very useful to classify whether some system, what fraction of it is like AGN and what. So everything is a composite, right? You have black holes and galaxies going together. So whether it's mostly dominated by black hole emission or is dominated by galaxy, that's how these are answered. Anyway, so we'll actually end here.